Hi everyone, and welcome to Meteorological Instrumentations. We're starting a new block here. We're going to talk about anemometers and anemometry. So we'll start out this first block with an introduction. This video will cover an introduction to anemometry. Anemometry comes from the Greek word anemimos, which means wind, and metron, which means to measure. Put them together and you got Anemimos metron, or anemometry, which is the study of measuring and recording the wind direction and the wind speed. And that includes all components, both the horizontal and also the vertical component. We'll talk about those here in a little bit. Wind is a vector, and vector, of course, has a magnitude and direction. So it's heading in some direction, and of course it has some magnitude. Typically we call the magnitude the wind speed, and of course the direction we call the wind direction. Because it's a vector, it's three-dimensional. So in space we can say that it has X, Y, and Z components. Usually whenever we measure the wind, we're more concerned, or we think about only the horizontal component, the X and Y, but there's also a Z component if you look at it Cartesian-wise. So the wind can be broken down into its three components if you look at the three-dimensional wind vector, which is V. The components are really important to remember these names or nomenclature. We use these components in meteorology all through developing theories of the motion and propagation of weather systems. So it's really important that you remember these components. The component of the wind that's in the east-west direction we call the U component. In other words, it's the change in the X direction with time. And for convenience, we point the X direction in the east direction. So any wind that moves east-west is the U component of wind. Likewise, we can look at the component of wind that's moving in the Y direction, whether it be positive or negative Y direction. And if the wind moves, or if something moves, the wind moves in the Y direction over a period of time, we say that that is the V component of the wind. The north-south component of the wind. So we've got U is the east-west, V is the north-south. And finally, the third component of the wind is the up-down component, which goes along the Z axis. So we would call that the W component. So we've got these three components, the U component, the V component, and the W component. Once again, I want to stress upon you, this may seem really simplistic, but this is extremely important in more advanced meteorological topics. So, of course, we usually look at only the horizontal component, both the U and also the V. We combine those to create the two-dimensional horizontal component of the wind. Usually the vertical component is very small. Not always. Some places, like in thunderstorms, the W component is huge in an updraft of a thunderstorm, or in mountain waves, mountainous areas where the wind is sloping down the mountain. The W component can be pretty significant, but a lot of times, or most times, 99% or maybe 90% of the time, the W component or the vertical component is rather small, and we can combine the U and V components to make the wind vector, and we use a big V to indicate the two-dimensional wind component. Wind speed, of course, is measured by an anemometer. Anemometer is more or less the general name that we give to any kind of device that measures wind speed. And it could be any of the components, individual components, or a combination of thereof. The anemometer was discovered or invented by two, I guess you would say, Renaissance people at independent times and independently. One was Leon Battista Alberti, came up with the swinging plate in 1450. And independently, Robert Hooke, who worked with Robert Boyle, came up with the same concept, the swinging plate, and used that to measure the wind. He did that in 1667. Units of wind speed are, of course, linear. It's the number of miles in an hour or length over some time. So we use a lot of different units depending upon what you're using it for. For example, most people are used to talking about the wind speed in miles per hour. If you're in aviation, we talk a lot about knots, which is a nautical mile per hour. In meteorology, since we deal with MKS units, all of our wind speeds are in meters per second. And you may also see centimeters per second. A lot of times they measure vertical velocities in centimeters per minute or centimeters per hour. And then in Eastern European countries, they use kilometers per hour to measure the wind speed at many airports, and you'll see that reported in the METARs. Here are some conversion factors for you. One that's really handy, since we use it quite a bit, is meters per second to knots, and back and forth. 1 meter per second is approximately 2 knots, or 1 knot is about 1/2 of meter per second. So you might want to stick that in the back of your mind, and it'll help you very quickly convert from one to the other. The first person to quantify wind speed. The anemometer was invented in the mid-second millennium, about 1450 or 1667, depending upon the inventor. But they didn't actually quantify it. They just looked at the deflection of a plate, and then based on that kind of just estimated the wind. But they really didn't quantify it. The first quantification of wind speed was done by Sir Francis Beaufort as the British conquered the seas. They needed to come up with a way of quantifying wind for their sailing ships. So Sir Francis Beaufort was in the British Navy and came up with the first objective scale. There's no equation for it. The equation that you see here is one that was developed later on in 1946, but it was the first attempt to quantify the wind, and we gave it the name the Beaufort scale after Sir Francis Beaufort. And it was somewhat of a subjective wind scale. It's based on things that you can see. The Beaufort scale went from 0 to 12. Later on, we came up with these conversions to meters per second and miles per hour. But basically, if you had a Beaufort scale 6, that was strong. And you could quantify that by when you see large branches in motion, whistling heard, and telegraph wires and umbrellas used with difficulty. So that was the first quantification of wind speed. Wind direction is measured by a wind vane, of course. That's an instrument to measure wind direction. And wind direction is always measured the direction at which the wind is coming from. And we use we measure it with relation to magnetic north, degrees from magnetic north. So that's what's reported in the METARs. It's with respect to magnetic north. But at airports, over control towers, when they report the wind, that's always in magnetic with respect to magnetic north. And the reason for that is runways are aligned with magnetic north. So you want to verify that the wind direction is the same as your landing runway. What's the difference between magnetic north and true north? We call that magnetic declination or variation. It's angular difference between true north and magnetic north. And as you know, magnetic north is not the same location as geographic or true north. And there is conversion factors back and forth depending upon where you are located on the Earth. The conversion is to go from magnetic to true. You have to either add or subtract the variation, in other words, the declination, depending upon where you are on Earth. And there are lines that are plotted on maps to indicate the declination or variation. And I can show you that on a sectional chart. Here is looking at the world, and it shows all of the angles, the isogonic lines that represent magnetic variation or declination. You can see the zero line goes through the central part of the United States, also goes through Eastern Europe, through Africa, and then back up through through Russia and China. So anywhere along that line, the magnetic north and true north would be the same. But you can see that there are variations or magnetic declination. If you're in the west part of the United States, say for example Juneau, Alaska, you would have 20 degrees between magnetic north and true north. Or if you're up in Newfoundland, you would have 20 degrees also. On the east coast of the United States, it's about 10 degrees. And then across western United States, it's also about 10 degrees. Depending upon whether it's east or west, you would add or subtract that. Here in Grand Forks, a little bit closer to home, you can see this is actually Castleton and Valley City region. You can see lines of variation, which we of course we called variation, and those variation lines here representing between 4 to 5 degrees east variation. So that's a little bit about measuring wind direction and wind speed. And in future videos, we'll talk about anemometers, cup anemometers, and propeller anemometers.